Maybe it's a marble rolling across a table, or perhaps a planet gracefully moving through space. It's such a basic concept, right? Rooted in what we see every day. But it holds these deep mathematical truths about geometry, about motion. And that image, that's actually where our first question for this deep dive came from. How does that simple act, a sphere rolling, connect to something like the constant pi and also to physical frequencies? And then the bigger question, how far can we really push that intuition? What happens when we try to apply it to, well, the quantum world, to this sort of spherical nature of quantum particles?
It's a really natural question, I think. It taps into that fundamental drive we have, doesn't it? To connect the world we can, touch and see to the universe's deeper, often hidden workings.
Exactly. So, look, our mission today isn't really about saying this idea is wrong. It's more like a shared journey. We're going to explore where this classical analogy, this rolling sphere, actually gives us some genuine insight, maybe in surprising ways, and also, crucially, where it kind of becomes a conceptual trap, where it hides the true nature of quantum reality, which is often, well, let's face it, completely counterintuitive.
You really can be.
Yeah. We want to give you a bit of a shortcut, help you get well-informed on this truly mind-bending topic. Okay, so to really get a handle on the quantum weirdness, maybe it helps to start with what we do know or think we know.
Ground ourselves first, yeah.
Let's firmly plant our feet in the familiar world of classical physics. That's where our intuition comes from, after all. We talk about pi all the time. But it's not just some useful number, is it? It's fundamental, a dimensionless constant.
Absolutely. It's that unchanging ratio, the circle's circumference divided by its diameter. C over D, always pi.
Always pi.
And because of that one simple fact, pi just gets woven into the very fabric of a sphere's 3D form. You find it everywhere. Well, the circumference of any great circle is 2r. The surface area, that's 4r. The volume, it's just there. Pi isn't just a number we use for spheres. It's embedded in how you even generate a sphere mathematically. It reflects something really deep about three-dimensional space.
And something else you mentioned is important here, the idea of two radians making a full circle.
Yes.
Sometimes people think, why not just stick with 360 degrees?
Yeah.
But radians are, in a way, more natural, aren't they? Linked directly to the radius.
Exactly. And that, too, for a complete cycle, that's not arbitrary. It turns out to be a really crucial bridge when we start thinking about waves and, eventually quantum mechanics.
Okay, so that's the geometry. What about motion? Frequency.
Right. So in the classical world, frequency isn't something an object just has intrinsically. It measures something it does, like how often it repeats a motion.
So if you're just sitting there, zero frequency.
Zero frequency. Classically, yes. But if it's moving, say rotating, we usually talk about two things. There's angular velocity, omega, measured in radians per second. And then there's ordinary frequency, f, measured in hertz, cycles per second.
And they're linked?
Directly, because one full revolution is 2 radians, omega always equals 2 times f equals 2 f. Simple relationship.
And if our sphere is rolling on a surface, say, without slipping, that no-slip condition is important.
Very important. It connects the rotation directly to the linear motion. The speed of the sphere center, v, is locked to how fast the edge is rotating. V equals radius times omega. V equals r.
Which means you can figure out its classical rolling frequency easily.
Completely easily. If you know its speed and its radius, you know the frequency. It's all deterministic. No quantum weirdness yet. Fully predictable.
Okay. Predictable. I like predictable.
Don't get too comfortable. But what's fascinating here, even in classical physics, is how we already separate a source from its field. That turns out to be really important later.
How do you mean?
Think about a spherical wave, like ripples from a pebble dropped in a pond, but in 3D. Or maybe sound spreading out from a small source.
Okay, yeah. Spreading out in all directions.
Right. The disturbance emanates from, ideally, a point source. But the wave itself, the disturbance, has this spherical shape.
Yeah.
And the energy spreads out over the surface of that expanding sphere, that four-core area we mentioned. So the intensity has to drop off, right? It gets weaker as 1 over r squared.
Makes sense. The energy's spread thinner.
Exactly. And you can write down a mathematical formula for this expanding spherical wave, R-E-I-K-R-E-A-I-I-K-R. It captures the spreading in the wave motion.
Okay, so the key insight there is?
The source can be point-like, basically zero size, but the field or the disturbance it creates has that definite spherical symmetry.
Ah, I see. And you're saying that anticipates something in quantum mechanics.
It does. This idea that a fundamental particle might be treated as a point, but its associative field, maybe its wave function, can have a shape, like spherical symmetry. It's a useful conceptual bridge.
Okay, bridge build now. Let's cross it carefully, because here's where things get really interesting, right? The quantum world. It seems to shatter our classical notions of particle and even frequency.
It really does. It started, arguably, with Louis de Broglie back in 1924. He had this, well, revolutionary idea
Which was?
that all matter, not just light, has wave properties. Everything. Electrons, atoms, baseballs, you, me.
Yeah.
Everything has an associated wave. We call them matter waves, or de Broglie waves.
That's the core of wave-particle duality, isn't it?
Absolutely. It's the bedrock. And he didn't just propose it conceptually, he gave us the math.
The de Broglie relation.
Exactly. The frequency of the matter wave, F, is the particle's total energy, E, divided by Planck's constant, H, so Fa.
Yeah.
And the wavelength, lambda, is Planck's constant, H, divided by the particle's momentum, P, so AhHP. The big takeaway is that everything has both a frequency and a wavelength. The line between particle and wave just gets incredibly blurry at this fundamental level.
So why don't we see, baseballs diffracting through doorways?
Ha! Good question. It comes down to momentum and Planck's constant. Planck's constant H is incredibly tiny. So for something macroscopic like a baseball, its momentum P is huge in comparison. That makes its de Broglie wavelength equal HP, absurdly small. Far too small to ever measure or notice.
But for tiny things, like electrons,
Now for electrons, especially if they're moving fast, their momentum is much smaller, so their wavelength can actually be comparable to, say, the spacing between atoms in a crystal. And that you can measure.
you can actually see the wave nature of electrons.
Oh, absolutely. It wasn't just theory for long. In 1927, Davisson-Germer did their famous experiment. They scattered electrons off a nickel crystal, and they saw diffraction patterns, just like you get with X-rays, which are waves. It was stunning confirmation of apole HP.
Wow.
And then there's the ultimate mind-bender, the double-slit experiment, but done with electrons.
Right, you fire them one by one.
One at a time. Each electron hits the detector screen as a tiny localized dot. Click. Particle nature, right?
Seems like it.
Wait for enough electrons to build up. And what pattern do you see?
An interference pattern.
Yeah.
Like waves passing through both slits and interfering with each other.
Exactly. Fringes of high and low probability. It means each individual electron somehow must have acted like a wave, gone through both slits simultaneously, interfered with itself before, poof, collapsing back into a particle at the screen.
It breaks your brain trying to picture that classically.
It does. You have to let go of the classical picture. So this brings up your earlier point. What about frequency when something isn't moving? Classically, it's zero. What about quantum mechanically?
Yeah, what happens then? Does an electron sitting still have a de Broglie frequency? Its momentum is zero.
Its de Broglie wavelength would be infinite, which is sort of weird. But the frequency question is fascinating. Here's the really startling non-classical answer. Yes, even a particle at rest has an intrinsic frequency.
It does. How?
You take de Broglie's F, ADA, and then you bring in Einstein's most famous equation for the energy of a particle at rest. E equals m euro.
Rest mass energy.
Right. Put them together. The frequency of a particle at rest, its Compton frequency, Fc, equals its rest mass energy divided by Planck's constant. Fc equals mach.
So its frequency comes just from having mass, not from moving.
Exactly. It's a fundamental frequency of existence, not of motion. This is a huge difference from classical physics.
So we need to distinguish these two frequencies. De Broglie frequency depends on motion, it's extrinsic.
Like how fast the wave crests are passing you by?
Whereas Compton frequency depends only on rest mass, it's intrinsic.
Correct. It's like an internal clock, ticking away just because the particle exists and has mass. Someone once coined the phrase, a rock is a clock.
I like that, a rock is a clock. So a classical sphere at rest, zero frequency. A quantum particle with mass at rest always has this Compton frequency ticking away, never zero.
Never zero, unless it's massless like a photon, which is a whole other story. But for massive particles, yes.
Okay, so this leads us to how physicists actually think about fundamental particles today, right? Like in the Standard Model. Are they tiny spheres?
No, definitely not. According to the Standard Model, which is our best current theory, fundamental particles like electrons and quarks are, well, they're considered point-like.
Point-like, meaning zero size.
Essentially, yes. No measurable size, no internal structure that we've ever detected. An electron isn't a thing in a field. It's better thought of as a single, quantized excitation or ripple of the electron field itself, a field that permeates all of spacetime.
So that old picture, the tiny solid ball spinning,
Yeah.
that's completely out.
Completely. People tried that early on,
Yeah.
but if you imagine an electron as a classical sphere small enough and try to make it spin fast enough to account for its observed magnetic properties...
Let me guess, faster than light.
Bingo. Points on its surface would have to exceed the speed of light, which is a major no-no according to relativity, so that picture just fails.
So when we talk about spherical nature in quantum mechanics, like the shapes of atomic orbitals, what is that then?
That's the shape of the wave function. It's the probability cloud, the description of where you're likely to find the point-like electron. It's a property of the field description, not the particle itself having a physical body.
Okay. Similar to the classical point source creating a spherical wave field.
Precisely. The symmetry is in the field, or the wave function, not necessarily in the source itself.
All right. And what about spin? You mentioned magnetic properties. Spin sounds like rotation.
Spin, yes, the name is suggestive. But quantum spin is truly weird. It's a uniquely quantum mechanical property. There's really no good classical analog for it.
No spinning top. No rolling sphere.
Not really. Those analogies break down very quickly. Spin is as fundamental to a particle as its mass or its charge. It just has it.
Okay, so what makes it so different? You said it's not classical rotation.
Well, first, it's quantized. It can only have specific, discrete values.
Like it's either this amount or that amount, nothing in between.
Exactly. An electron, for instance, is always a spin 12 particle. Always. You can't make it spin faster or slower. Its spin magnitude is fixed. It just is spin 12.
That's weird. A classical top can spin at any speed.
Right. Second, it's intrinsic. It doesn't arise from something else rotating. It's just part of what the particle is. And third, the rotation aspect is bizarre. To get a spin 12 particle's wave function back to its original state, you don't rotate it 360 degrees.
No.
You have to rotate it 720 degrees. 2 full turns.
Wait, what? 720 degrees? How does that even work?
It's deeply weird. It's as if the quantum state has this hidden twist that only undoes itself after 2 full rotations. A classical object is back to normal after 360. This 720-degree symmetry is fundamentally non-classical.
Where does that come from?
It actually emerges naturally when you combine quantum mechanics with Einstein's special relativity. The Dirac equation, which describes relativistic electrons, automatically includes spin 12 in this strange rotational property.
Okay, my head hurts a little. So we've got this point-like particle, intrinsic frequency, quantized spin with 720-degree symmetry. This sounds nothing like our nice, simple rolling sphere.
Not much like it at all, on the surface.
So what does this all mean for our original analogy, the rolling sphere? Is it just completely wrong, a bad comparison we should just ditch?
Well, here's where it gets really surprising. You'd think, based on everything we just said, the analogy is purely metaphorical, maybe even misleading.
Yeah, sounds like it.
But physicists discovered something remarkable. There's actually a deep, rigorous mathematical connection, an isomorphism, they call it.
A mathematical connection between the classical rolling sphere and quantum spin.
Yes. Specifically between the classical kinematic equations, the math describing how a sphere rolls without slipping on some surface, and the quantum dynamical equations describing how a spin 12 particle, like an electron, precesses or wobbles when it's in a magnetic field that changes over time.
That sounds unlikely. How can those be related?
It's not just a vague resemblance. It's a formal structural equivalence between the two sets of differential equations that govern these seemingly different systems.
Wow. Okay, can you give an example? What maps onto what?
Sure. So imagine the path the sphere traces as it rolls. The length of that path, the arc length S, mathematically plays the role of time t in the quantum system.
Okay, time becomes distance.
Right. And the sphere's angular velocity, how fast it's spinning, omega, that corresponds mathematically to the external magnetic field, B, that the quantum particle is experiencing.
Angular velocity maps to magnetic field. Weird.
It is. And the sphere's orientation in space, which way it's pointing, that directly corresponds to the quantum particle's spin state.
Yeah.
We often visualize that quantum state on something called the Bloch sphere.
The Bloch sphere, right? That's like a map for spin directions.
Exactly. So the orientation of the classical sphere on its surface maps directly onto a point on the Bloch sphere representing the spin state.
Is this just a mathematical curiosity, or is it useful?
Oh, it's incredibly useful. It's a legitimate computational tool. There's a famous problem in quantum mechanics called called the Landau-Zener problem. It calculates the probability that a particle's spin will flip direction as it passes through a region where the magnetic field is changing.
Okay.
You can actually solve that quantum problem by mapping it onto a classical sphere, rolling along a very specific path. It turns out to be something called a Cornu spiral. You calculate how the classical sphere's orientation changes as it rolls along the spiral path.
And that gives you the quantum answer.
Precisely. The final orientation of the classical sphere tells you the quantum probability of the spin flip. It's a genuine computational shortcut.
That's actually amazing. So the analogy isn't just fluff. It has real mathematical teeth.
It really does. And that's why it can be so powerful for building intuition, despite the conceptual differences.
It gives you something tangible to visualize, right?
Right.
It's way easier to picture a rolling sphere than, well, an abstract spinor in Hilbert space.
Yeah, exactly. Much easier. And it's particularly good for understanding certain subtle quantum effects, like geometric phases, sometimes called Berry phases.
One of those, quickly.
It's basically a phase shift, like a slight rotation in the quantum state's internal clock that a quantum system can pick up when its environment changes slowly and then returns to the starting point. The surprising thing is, the amount of phase shift depends only on the geometry of the path the environment took, not on how fast it happened.
And the rolling sphere helps with that.
Perfectly. The classical sphere rolling around a closed path on a surface also picks up an extra angle twist called Henne's angle that depends only on the path's geometry. The mathematics is identical. It makes the abstract quantum idea much more concrete.
Okay, so the analogy has this surprising mathematical depth and is great for visualization and understanding geometric phases. But you said it hits a wall.
If we connect this to the bigger picture, despite its mathematical elegance, the rolling sphere analogy ultimately fails as a complete physical model. And the reasons why are fundamental. The limitations aren't just minor details, they go right to the heart of what makes quantum mechanics quantum.
Right. Let's talk about where it breaks down. What's the first major failure?
Quantization. We talked about how quantum spin comes in fixed packets, spin 12, spin 1, etc. The classical rolling sphere analogy has absolutely no way to explain why. A classical sphere can be made to spin at any rate you like. There's no inherent allowed spin speed. It completely misses the discrete, quantized nature of spin.
Okay, so it fails on quantization. What else?
Superposition and measurement. This is a huge one. A classical sphere always has a single, definite orientation. It's pointing this way right now.
Makes sense.
But a quantum particle, before you measure its spin, can exist in a superposition of states. It can be, in a sense, both spin up and spin down at the same time.
The Schrodinger's cat idea applied to spin.
Kind of, yes. It exists in this probabilistic limbo until you perform a measurement. Then, and only then, it randomly chooses one definite state, spin up or spin down, and the wave function collapses.
And the rolling sphere has no way to model that.
None at all. You can't have a sphere that's simultaneously pointing in multiple directions until you look at it. The analogy completely lacks this probabilistic core and the whole measurement problem.
Right. That seems like a fundamental gap. Is there more?
Oh, yes. The most profound failure, arguably, is entanglement and non-locality.
Oh. Einstein's spooky action at a distance.
Exactly. You can have two quantum particles, say 2 electrons, created in a special entangled state. They're then described by a single unified wave function, even if you separate them by light years.
Okay.
If you measure the spin of one particle, say you find its spin up, you instantly know, faster than light could travel between them, that the other particle, wherever it is, must be spin down.
There's this perfect correlation built in.
A perfect, instantaneous correlation that defies any classical explanation based on local properties. You simply cannot model this with two separate classical rolling spheres, no matter how cleverly you link them initially. Each sphere evolves independently based on its local conditions. Quantum entanglement shows reality as fundamentally non-local and interconnected in a way classical physics can't handle.
So the classical sphere analogy, while mathematically useful in specific contexts, ultimately fails to capture quantization, superposition, measurement, and non-locality, basically, all the core mysteries of quantum mechanics.
Pretty much, yes. It's a powerful shadow, but it's not the real thing.
These limitations, they really highlight this tension, don't they? Our very human desire for a reality we can picture, something tangible, maybe mechanical, versus the sheer abstractness of quantum mechanics.
Absolutely. And that tension hasn't gone away. It's actually fueled the development of alternative interpretations or even alternative theories that try to recover a more physical or intuitive picture.
Like what? Are there theories that try to make quantum mechanics less weird?
Well, one prominent example we touched on briefly is the de Broglie-Bohm pilot wave theory, also known as Bohmian mechanics.
Right. De Broglie started it, Bohm revived it. What's the core idea again?
It basically says, yes, there are particles, real point-like particles, that always have definite positions and follow definite paths, trajectories.
Okay, that sounds more classical already.
It does, but crucially, it also posits a real physical pilot wave, which is mathematically the same as the standard Schrödinger wave function that exists everywhere in space and actively guides the particle's motion.
So, two entities, particle and wave, both real.
Both real and interacting. So in the double-slit experiment, the particle itself goes through only one slit, just like a classical object, but its guiding wave goes through both slits, interferes with itself, and creates regions where the wave intensity is high or low. The wave then steers the particle towards the high-intensity regions.
So the interference pattern comes from the wave guiding the particle.
Exactly. And the apparent randomness of quantum mechanics in this view just comes from our unavoidable ignorance of the particle's precise starting position within the wave. If you knew the exact starting point, you could predict its exact path deterministically.
That sounds appealingly simple, in a way.
Yeah.
It gets rid of the measurement problem and superposition, sort of. What's the catch?
The biggest catch is explicit non-locality. The guiding wave connects everything. So the theory states that the velocity of any one particle can depend instantaneously on the positions of all other particles described by the same wave function, no matter how far apart they are.
There's the spookiness again, just made explicit.
Right. It embraces non-locality head-on. Also, trying to make a fully relativistic version of pilot wave theory that incorporates particle creation and annihilation, like in the standard model, has proven extremely difficult. It's not the mainstream view, but it shows people are still trying to find a more intuitive picture.
Interesting. Are there other attempts, maybe ones that take the sphere idea more literally?
There are, though they tend to be much more speculative. These are often called vortex models of elementary particles.
Vortex models, like whirlpools.
Kind of, yes. The idea actually has a long history. Back in the 19th century, Lord Kelvin proposed a vortex theory of the atom. He imagined atoms as stable, knotted vortices like smoke rings in a hypothetical fluid called the luminiferous ether that was thought to fill space.
That sounds pretty wild. Didn't work out, I assume.
No, the ether theory died out. But the core idea of particles as stable, localized whirlpools or vortices in some kind of underlying vacuum medium keeps recurring in various forms.
So how would that explain particle properties?
Well, the idea would be that the particle's mass comes from the kinetic energy tied up in the swirling motion of the vortex.
Okay.
And spin would be interpreted as the literal angular momentum of this vortex.
Taking the spin name literally.
Very literally. These models are appealing precisely because they offer a fully mechanical, visualizable picture. You can almost imagine these tiny whirlpools interacting. It satisfies that intuitive craving for a tangible reality. But they face enormous challenges. So far, none of these vortex models have come close to reproducing the incredibly precise predictions of the standard model across the vast range of experiments we've done, explaining all the different particles, their interactions, quantum field effects. It's proven incredibly difficult, maybe impossible, within that framework.
So they remain highly speculative.
Very much so. But they perfectly illustrate that deep-seated human drive, that desire to find explanations we can grasp, explanations rooted in the mechanics of the familiar world, even when quantum mechanics keeps telling us reality might be far stranger than that.
Yeah, it really brings us back to the limits of analogy.
I think the ultimate conclusion here, really, is that the classical analogy of a rolling sphere, however mathematically useful it can be in places, is fundamentally a projection. It's like a shadow.
A shadow?
Yeah, a shadow cast by the true quantum reality, which is higher dimensional, probabilistic, inherently non-local, onto the flat wall of our everyday three-dimensional deterministic experience.
That's a powerful image, a projection.
Analogies like this are absolutely indispensable. We need them to ask the first questions, to frame problems, to build that initial bridge of intuition. They're incredibly powerful conceptual tools to get us started.
But they aren't the destination.
They aren't the destination. To achieve that truly deep, accurate understanding of the physical world, the one described so successfully by modern science, Well, eventually you have to be willing to let go of that classical scaffolding, however comfortable it feels.
You have to embrace the weirdness.
You have to embrace the weirdness, and perhaps more importantly, embrace the abstract mathematical formalism, the Schrödinger equation, the Dirac equation, Hilbert spaces, operators. This isn't just inconvenient math getting in the way of some deeper mechanical reality.
It is the description.
As far as we know, yes. It is the most accurate, the most predictive, and the most complete description of reality that humanity has ever developed.
So that journey, from the simple, tangible comfort of the rolling sphere to the abstract, sometimes baffling power of the wave function.
That's the journey physics itself took throughout the 20th century. And it's really the same journey every student of nature, everyone who wants to understand the universe at its deepest level, must ultimately undertake themselves. You have to learn to speak the language the universe seems to use.